Hello everyone, welcome back to RareChem Official. Today we are going to discuss about molecular orbital theory. It was proposed by Hund and Mulligan to explain the paramagnetic nature of oxygen molecule. 2s2 2p4 is the valential configuration of oxygen, and this is one oxygen atom. This is another oxygen atom. Oxygen has two unpaired electrons. One unpaired electron, it forms sigma bond with other unpaired electron. One more unpaired electron, it forms 5 bond with the other unpaired electron whenever occurs sideways overlap. Double bond is formed between two oxygen molecule, two oxygen atoms. Here, two unpaired electrons participated in bonding. No unpaired electrons. According to VBT, it is diamagnetic. It is the one of the drawback, but it behaves like a paramagnetic. To explain the paramagnetic nature of oxygen molecule, molecular orbital theory was proposed by Hund and Mulligan. The electrons in molecule are present in molecular orbitals as the electrons of atoms are present in the various atomic orbitals. If two atoms combine together, it forms molecule. Whenever two atomic orbitals combine together, it forms molecular orbital. Here, this is one atomic orbital, this is other atomic orbital. This is the nucleus, electrons revolving around the nucleus. Here, electrons influence of one nucleus. This is molecular orbital. Here, electrons revolving around the nucleus. Here, electrons influence of two nucleus. Molecular orbitals are formed by linear combination of atomic orbitals of comparable energies and proper symmetry. Comparable energies means similar energies. 1s orbital can combine with 1s orbital. It can't combine with 2s orbital because 1s has similar energies, 1s 2s has different energies. Molecular orbital is polycentric. Example, an electron in molecular orbital is under the influence of two or more nuclei. Here, atomic orbitals, electrons influence of one nuclei, but in molecular orbital, electrons influence of two nuclei. The number of molecular orbitals is equals to the number of molecular orbitals formed is equals to the number of combining atomic orbitals. Here, these are the two atomic orbitals. When combining together, it forms two molecular orbitals. Number of atomic orbitals is equals to 2. Number of molecular orbitals is 2. One is the bonding molecular orbital, other is the anti-bonding orbital. Energy of atomic orbital is here, but bonding molecular orbital is this much, means it lost some energy. Anti-bonding molecular orbitals gained some energy. It is here, means it is stabilized, and anti-bonding orbital is destabilized. It may be noted that the bonding molecular orbital is stabilized to the same extent as the anti-bonding molecular orbital is destabilized. Bonding orbital is stabilized, anti-bonding molecular orbital is destabilized. It means the energy lost is equals to the energy lost by bonding molecular orbital is equals to the energy gained by anti-bonding molecular orbital. Here, the energy lost means this is energy of atomic orbital. Here, bonding molecular orbital means it lost some energy. Lost by bonding molecular orbital is equals to energy gained by anti-bonding molecular orbital. Order of energies for various various orbitals is bonding orbital is less than non-bonding orbitals is less than anti-bonding orbitals. Anti-bonding orbitals has more energy. The molecular orbital like atomic orbitals are filled in accordance with Aufbau, obeying the Pauli's exclusion principle and the Hund rule. Above principle states that is lower energy orbitals fills first, then higher energy orbitals. Means 1s orbital first we have to fill, then 2s, then 2p, and etc. Pauli principle states that is each orbital can accommodate two electron with opposite spin. Means if it is s orbital, it can accommodate two electrons with opposite spins. This orbital can accommodate two electrons not like similar spin. Kunz rule states that is first electron fill the orbital with one electron, second electron then we have to fill. Means first electron fill first in each orbital, then second electron we have to fill with opposite direction. According to wave mechanics, the atomic orbitals can be expressed by wave functions. Means atomic orbitals like wave. See, two atomic orbitals, whenever we addition, the amplitude increases here whenever addition of two atomic orbitals. Whenever two atomic orbitals subtract, we amplitude of this orbital, means molecular orbital's amplitude is decreases. Quantitatively, the formation of molecular orbital can be understood in terms of constructive or destructive. Here, whenever we addition of two atomic orbitals, this is constructive manner, means it increases the amplitude, so it is constructive. But two atomic orbitals, whenever we do subtraction, this amplitude is decreases, means destructive, means decreases. Psi AB is equals to psi A plus or minus psi B, means psi A plus psi B, psi A minus psi B. These are the wave functions. Means whenever two atomic orbitals combine, it is constructive manner. Whenever two atomic orbitals subtract, that is destructive manner. The electron density in bonding molecular orbital is located between the nuclei of the bonded atoms. See, this is the two atomic orbitals. Whenever it forms molecular orbitals, the electron density between two nuclei. But in bonding molecular orbital is located between two nuclei of bonded atoms. See, this is the electron density between two nuclei in bonding molecular orbital. But anti-bonding molecular orbital, the electron density is away from the space. Means this is two atomic orbitals. Whenever it combines molecular orbital, it forms, right? See, electron density away from each other. One nodal plane is present. Nodal planes, next atomic chapter we will discuss. Atomic structure. For less than 14 electrons, lithium 2, beryllium 2, boron 2, B2, these are the examples. For less than 14 electrons are equals to 14 electrons. The increasing order of relative energies of molecular orbitals for less than 14 are equals to 14. Whenever molecules has less than 14 or equal to 14, this configuration or increasing order of relative energies, we have to use this. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, 5, 2px, 5 equals to, these are the two degenerate orbitals. 5 2py, sigma 2pz, 5 star 2px equals to 5 star 2py, sigma star 2pz. For more than 14 electrons, O2, F2, like that. For more than 14 electrons, if present in molecule, we have to use this increasing order of relative energies. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, 2pz, sigma 2pz. Here, before phi 2px equals to phi 2py came in less than 14 electrons or equals to 14 electrons, but more than 14 electrons, these two orbitals only interchange. So phi 2px equals to phi 2py, phi star 2px equals to phi star 2py, sigma star 2pz. If take N2 molecule, here 7 plus 7 equals to 14. Here we discussed for less than 14 electrons are equals to 14 electrons, we have to use this increasing order of energies. Here this configuration we have to use here, because here 14 electrons present in N2 molecule. If observe the configuration of nitrogen is 1s2, 2s2, 2p3. First we have to draw atomic orbitals 1s2, 2s2, 2p3. This is one nitrogen atom, this is other nitrogen atom. 1s2, 1s2, these are the relative energies, means similar energies. 1s2 means 1s orbital, these are the two atomic orbital combined together, it forms two molecular orbitals, right? This is sigma 1s, sigma star 1s. 2s2, this is the 2s2, this is one nitrogen atom, if two combine together it forms two molecular orbitals, that is sigma 2s, sigma star 2s. In 2p3, these 2p combined together it forms these molecular orbitals, phi 2px, phi 2py, sigma 2pz, phi star 2px, phi star 2p, by sigma star 2pz. We have to fill electrons 14, total number of electrons are 14. First we have to fill in this orbital 2, 4, 6, 8. Here these are the two degenerate orbitals. First electron we have to fill in each, and next we have to fill second electron in each. Next sigma 2pz, 2pz 2 electrons. Totally 2, 4, 6, 8, 10, 12, 14. The bond order is number of bonding molecular orbitals minus number of anti-bonding molecular orbitals divided by 2. Here if use this configuration, number of bonding orbitals how many? 2, 4, these are the star symbol means that is anti-bonding. Here bonding orbitals are 2, 4, 6, 8, 10. Anti-bonding orbitals 2, 4. 10 minus 4 by 2 equals to 6 by 2 equals to 3. The bond order is 3. Means first in examination point of view they will ask only bond order, no need to draw molecular orbital energy diagram, but but we want to know, right? So we are discussing, but in examination point of view these two configurations means for less than 14 or equals to 14 electrons we have to use this configuration, and for equals more than 14 electrons we have to use this configuration. These two we have to remember. If you remember these two, we can solve any bond order related questions. Here no need to draw this molecular orbital energy diagram. First we have to count total number of electrons in a molecule. Here nitrogen N2 molecule has totally 14 electrons. First we have to fill this configuration is for less than 14 or equals to 14. So I fill like this. 1s2, first each orbital, first we have to fill 1 2 4 6 8. Here these are the two degenerate orbitals, right? First we have to fill 1 1 each, and next we have to fill like this. And how many electrons? 2 4 6 8 10 12, remaining 12 to 2. How many electrons present? 14. So 14 electrons we filled, right? 2 4, these are the sigma star. Here bonding orbitals are 2 4 6 8 10. 10 minus how many anti-bonding orbitals? 2 4 6, and divided by 2 equals to 3. The bond order is 3. Like that we can solve. If take O2 molecular orbital energy diagram, O2 molecule has 16 electrons. It is more than 14 electrons, right? If we look molecular orbital energy diagram for O2 molecule, these are the 1s, this is 1s orbital, this is 1s orbital. These are the two atomic orbitals can combine. These two atomic orbitals can combine with each other and it forms molecular orbitals. And these are the two s orbitals, atomic orbitals. These are the molecular orbitals. If draw molecular orbital, O2 molecule has 16 electrons present, right? If fill 16 electron in each orbital, 1 is 2 4 6 8, and remaining 8 we have to fill. 8 10 11 12 13 14 15 16. Because these are the degenerate orbitals, means same energy. First electrons fill in each orbital, then we have to fill second electron. If configuration, if observe 2 4 6 8 10 12 14 16. Here number of bonding orbitals are 2 4 6 8 10 10. How many anti-bonding electrons? 2 4 5 6. 6 10 minus 6 by 2 equals to, we got the 2. Bond order is 2 between two oxygen atoms. If write without drawing molecular orbital energy diagram for O2 or any molecule, without, here O2 has total electrons are 16. So we have to fill, first we have to remember two configurations, means one is for equals to 14 or less than 14, and one is more than 14 electrons. We have for that we two configurations we have to remember. This is more than 14 electrons. This is the configuration for more than 14 electrons. Here if fill 2 electrons, 16 electrons in 16 electrons, 2 4 6 8 10 11 12 13 14 15 16. Here two unpaired electrons are present, so it is paramagnetic. In nitrogen, electrons are paired, so it is diamagnetic. So this is what Hund and Mulliken wants to explain. Because oxygen has unpaired electrons, it behaves paramagnetic nature, but according to VBT it is diamagnetic. That is one drawback of valence bond theory. So That's all for today. Thank you for watching.